for us because it converts the carbon-oxygen bond in the aldehyde or ketone to an alkene. And that's useful for us because, as we saw in Organic 1, there's a lot you can do with alkenes. So starting from an aldehyde or a ketone, we can jump into alkene chemistry. In addition to this, this also creates a new carbon-carbon bond. So that's, what does that mean for organic chemistry? We discover a reaction that creates a new carbon-carbon bond, we get a Nobel Prize, and now we can make more complex molecules and name it after. Right? So late 70s, 1979, Nobel Prize went to those that discovered the lytic reaction. Now, the reagent that you're going to see on the reaction arrow is referred to as a phosphorus ylide. Now, the name is not important, but its structure is. So, your ability to recognize this, you should be able to recognize this because it looks very strange. It is essentially a Schwitter ion complex, but the carbon now is stabilized with a negative charge. So when we think about the mechanism of this process, and we combine an ylide, a phosphorus ylide, with an aldehyde or a ketone, we're now thinking about, just like we did with Gringer's reagents, the carbon as the nucleophile. And that's unusual. Right? Carbon normally is the electrophile, those are the reactions we talk about. And so by changing up the dynamics of the charge, we can view these ylides as nucleophiles, carbon-based nucleophiles. Now, this CR2 fragment really needs to come from a good SN2 substrate. So the creation of the ylide is a two-step process that involves two reactions that we've already seen. Are we okay with pH? We know what pH means? What is pH? Just a benzene ring, right? So the two-step process to create these, it starts with an SN2 reaction, which is why we're sort of limited in which alkyl groups we can use. So for example, if I take a benzyl bromide, and we know how to synthesize this from benzene, right? We can take a Friedel-Crafts alkylation and then do a benzylic halogenation with NBS. So you were asked to do that on the last exam. So here the SN2 reaction, that's simply attack and elimination. And in this case, once I do that, that's going to create for me an intermediate that has a positive charge. And so that's stabilized by the bromide that we just kicked off. And what we're trying to do here is notice that in the ylide, I've only got two groups attached. But at this point, I have three. Which of those three do you think will be the easiest to remove to get down to two? You think it'll be easiest to just remove the benzene ring from that carbon, or one of the hydrogens?
Hydrogen.
And how do we remove hydrogens? Starts with B, ends with ACE. ACE, right? Now this is a hydrogen that's bound to a carbon, so is that going to be very acidic? Say bless you, that response. Hydrogen bound to a carbon, is that going to be acidic? Sometimes they are. Most of the time, not. So that's going to require us to use a very strong base, one that we've seen before. So we said that anytime we use these alkylithium reagents or Grignards, in the absence of a carbon-oxygen double bond, they go after the most acidic proton. So normally we'll use these to create, let me just grab the one over here. that allows us to create the negative charge at the carbon. Okay. So it's at this point that we got a stable reagent that we can now add to our aldehyde or ketone. Now, the mechanism that you see from book to book sometimes is different, but they're essentially saying the same thing. The way I like to show this reaction is to draw our reagents in a suggestive fashion as to how they're going to attack. So we just bring in an aldehyde. If we look at the carbon-oxygen double bond, which end of that double bond is positively charged to some extent? The carbon or the oxygen? The carbon. So the negative charge on my millet, that carbon, should be attracted to the carbon, which now has a partial positive charge due to the bond dipole of my aldehyde or ketone. So let's just go ahead and use this particular billet. So remember we said that in the aldehyde or ketone, if I needed a nucleophile, I'll use the lone pair on the oxygen. So we'll have some attraction to the positive charge of that billet. So normally what we would think about is, we said, well, if the nucleophile has a negative charge, we don't need acid to start this process. That nucleophile can go ahead and attack on its own. And what we've normally done at this point is break open the carbon-oxygen double bond, right? Yes? We're not going to change that, but what we're going to do is save ourselves arrow and break open that bond and go ahead and send that over to that positive charge. So we're essentially going to create a four-membered intermediate. Have a nice little square shape here. It's helpful to keep track of everybody that was on your original aldehyde or ketone, as well as who's hanging off of your billet. So overall, my reactants originally were neutral, negative and positive. So my intermediate should also be neutral. And so what we see here is now a collapse of this four-membered ring to create my product, which is an alkene. There's the carbon of my billet. This is the product that I'm interested in. And that phosphine oxide that we create normally just goes to waste. We get a mixture of isomers. I'm not going to ask you to be aware of which ones are preferred. It's not as simple as saying that trans is preferred over cis. It's due to the electron withdrawing or electron donating nature of the groups that are on your billet. Typically what we see with electron withdrawing groups, in this example, that the Z isomer, or the E isomer rather, is going to be preferred. Electron donating groups typically gives the Z. But again, just draw one of the alkenes, that's all I'm looking for. Right? So mechanistically, the only thing we're really changing here is instead of breaking that carbon-oxygen bond and giving ourselves a negative charge and propagating it, it now has an attraction to my reagent. And from that, we allow for the collapse of those two bonds to generate my alkene. So this is the major organic product that we'll be interested in, the carbon-carbon double bond. Any questions with the generation of the ylid, use of the ylid to make the alkene? going to be another reaction that I'll try and avoid using in synthesis problems simply because it's hard to sometimes see when I use a pitting reaction. So normally this is going to be something that I'll just limit us to the mechanism or just a one-step problem, just like the kiln. All right, so let's take a look at a couple of problems, sort of working forwards, working backwards, to see if we have a gist of what's going on. Talk amongst yourselves.